Okay, it's been quite some time, but if you recall when we last met, I was mentioning the fact that this expansion chamber with an inlet and an outlet tube is equivalent to what we did a little while ago, which is the 3 media case with a finite width, the second medium having a finite width which is x equal to L. So this corresponds to basically the case where I have a characteristic impedance rho 1 C1, this is one fluid, rho 2 C2 another fluid, and we had derived with rho 3 C3 as a third fluid. But in this particular case, we are going to show in the Muffler case that this rho 3 C3 is a special case where that is equal to rho 1 C1. So the idea is to show that the transmission power transmission coefficient for both of these cases is identical. So let's look at how to prove that. So what we are basically going to do is to derive the relation for the pressure and transmission coefficients, and instead of writing the continuity of the pressure and the mass velocity individually, what we are going to do is to look at those ratios at x equal to 0 as well as at x equal to L. So let's, assuming plane waves, we have the following expressions for impedance. On the left hand side pipe which is coming in, y0 basically is C by S0, where S0 is the cross section area of the pipe. Y1 is C by S1, where S1 is the cross section area of the chamber. And again we are assuming the outlet pipe has the same area of cross section as the inlet pipe. So I have Y0 into Pi plus PR, which is the pressure, and my Pi minus PR. Remember, Pi minus PR by Y0 is basically my mass velocity expression. So this is pressure divided by mass velocity, which is what we are looking at. So if I look at continuity across the expansion chamber, then I have Y1 times PA plus PB, which is the notation that I am using for the pressures. The mass velocity is PA minus PB by Y1, and the Y1 of course comes to the numerator. So this is at x equal to 0. Now at x equal to L, what we are going to have is I have Y1 PA e to the IKL plus PB e to the minus IKL, which is the reflected wave, divided by PA e to the IKL minus PB e to the minus IKL. So this is of course the impedance on the left hand side, which is continuous across into the exit pipe. But remember, since I have an infinite pipe, the PT is the pressure at the top, and the velocity, mass velocity, is PT by Y0, therefore this is simply equal to Y0. So we have these two equations, and what we really want to find out, it's easy for us to find out first, is PR by PI, which is the pressure reflection coefficient. Once we know that, we can then find the transmission coefficient from the expression. So let's see what is PR by PI, and if I'm just going to write down this, I request you to go through the algebra, do the elimination, and then prove to yourself that PR by Pi, which is the reflection coefficient, can be written in the following form: minus I times the following expression, which is, just a minute, I have Y1 by Y0 minus Y0 by Y1 sin KL divided by 2 cos KL minus I Y1 by Y0 plus Y0 by Y1 sin KL. So you can see that this is the form for the pressure reflection coefficient. Of course, this is a complex quantity, so it has both a phase as well as a magnitude. So what the phase basically tells you, the phase that you are going to find from this is the phase relationship between the incident and the reflected wave. Now in order to find the power coefficient T pi, this is going to be 1 minus the magnitude of R square, which is basically the reflection coefficient square. Now if you carry out the algebra, and I am again going to not go through the details, so we can now find an expression for t pi which is going to be of the form, the final expression turns out to be a rather neat looking expression, which is 1 plus 1 by 4 y1 by y0, 1 by 4 here, minus y0 by y1 the whole square, sine square kl. So this is the transmission coefficient. So this is the fraction of the incident power that is going to be transmitted into the exit pipe. Now if you recall that from the earlier class, the last class that we had before this break, I had shown you the expression for an expansion chamber from the transfer matrix method. We wrote down the transmission loss essentially as 10 log base 10 1 plus 1 by 4 m minus 1 by m the whole square sine square kl. So this is what was the expression for transmission loss that we derived. Remember, m is the area ratio, so m is S1 by S0, which of course is Y0 by Y1. Okay, so you can see that, of course, except for the fact that this is flipped, remember the transmission loss definition is basically the incident power by the transmitted power, whereas this T pi expression basically is what is the fraction of the incident power that is basically transmitted, so therefore it has a reciprocal relationship. But fundamentally you can see that what we derived from the transmission matrix method to derive the transmission loss is effectively the same that we derived from simple first principles of wave reflection and transmission. What I want you to do is to basically go back, look at the expression that we derived for the three-layer technique, and you will see exactly the same expression that is sitting there, except that instead of y1 and y0 you have that in terms of the characteristic impedances, which is r1, r2 instead of y1 and y0. So please go and look at that, and until we meet again, goodbye.